Okay, are there any questions before we get started? Okay. We've been working on subspace projection method. Essentially, we start out with a problem in an infinite dimensional Hilbert space that we can define as such, and then we cannot solve this problem on the computer, so we work on subspace projection. One way is to expand, say, this in terms of a basis set. And this is a good approximation to this original function in the infinite dimensional Hilbert space. This is originally in the infinite dimensional Hilbert. It's not computable, so we make approximations like this. And we might want to use a notation that after we substitute this in here, then we get an equation something like this. And then we test this equation with Wm. And n might go from 1 to n, so that eventually we get a system that looks like this. This is G. Okay, this must be and we choose n to be 1 to n, so that finally this is a square matrix system. So this is equivalent to a matrix system of such a kind where this is n by n, and this is n by 1, this is n by 1, and becomes solvable on the computer. And once you solve this on the computer, then you get your A. After having found your A, you can go and find an approximation for F. Okay, so this is essentially the subspace projection method. And you can think of L can be an integral or differential operator. Or it can be an integral differential operator, a mix of the two. And hence, all linear integral equation and all linear differential equation can fall under this category. So if you apply this method to solve differential equation, it's usually called the finite element method. And actually it was first used by Galerkin in about 1910. It was quite long ago. And of course there are a whole slew of other Russians who use this method, and sometimes there are names like Petrov, and then names like Kravchuk. And then these are around 1930 or so. And Kravchuk was particularly given the credit of applying the method of moments to solve integral equation. And then in the 1960s, we had people like Harrington taking up such idea in the US in 1960s. Because by the time 1960 comes, computers are quite important, and we can do a lot of these things on computers, and this method becomes of great interest. So when f sub n are orthogonal, this is very simple. We can also define an identity operator that is an outer product of fn and fn and so on. N is equal to 1 to n, okay, and this is like an outer product between the bases if Fn is orthonormal. Okay, and a simplest example is this one, like if x hat, y hat, and z hat is used as a basis, then we know that in 3 dimensions we can define this identity operator, which is just this one, plus z hat 2. Okay, and it's not restricted to Cartesian coordinate system. You can also use this for spherical coordinate system, and hence this would look something like theta hat plus phi hat plus r hat. And you often see this in the dyadic Green's function, that when you have something like this, and in the far field this could often be approximated like I minus k over k squared in the far field, and then this can be written as I minus k hat g, and this is essentially r hat. Okay, this is essentially r hat, and hence you find that this essentially is theta hat plus phi hat g in the far field. Okay, so the dyadic Green's function becomes something like this in the far field, which means that we have a transverse field. Electromagnetic field is also known as a transverse field because the field is always transverse to the direction of propagation. That's why it emerges in this manner. Okay, E is proportional to this, and then it's equal to that. Okay? So, I'd like to talk about the case of non-orthonormal bases. Non-orthogonal bases or basis functions. What happens if we do not have orthogonal bases? And that is usually the case if we do a lot of computation, because it's quite hard to design orthogonal bases. So how would this mathematics go if the bases are not orthogonal? Let's assume that, as I have written in my lecture note here, that we use a set of bases that are not orthogonal. Okay, how do we find this coefficient a sub n? A simple way to find this coefficient a sub n is to just multiply this equation with another set of complete bases in the finite dimensional space. N might be 1 to n. Okay, so in this finite dimensional subspace, you end up with the equation something like this. It's equal to n Wn Gn A. Okay, you end up with something that looks like that. And then this equation can be written as a matrix equation. I can call this f of m. Okay, and I can call this Gmn. Okay, and then I essentially have a matrix equation f is equal to G dot A, and this matrix has a special name. It's usually called a Gram matrix. It's usually called a Gram matrix, and this matrix would have been a diagonal matrix if this has been chosen to be a set of self-orthogonal vectors, and this would have been a diagonal matrix if this has been orthogonal. But we don't choose this to be orthogonal. In general, this is not diagonal. So from this equation, you can get that G is G inverse dot F. Okay, G inverse dot F. And if you want to get back the original solution, which is this one over here. Okay, so the solution is that the vector f can be written as a sum of n, Gn A sub n. Okay. We can write this in a more compact notation so that I can write the right hand side in a more compact notation by stacking all this thing into a vector. I can put all of this into a vector and hence write this as a vector within a vector. So this is a column vector dotted with A, another column vector. I can call this a transpose vector. So that when this multiplied with this, I get this back. Okay, can you accept this notation? Think of this as a column vector. Think of this being stacked up in a column vector, but in a transpose direction. So this is just a stacking of a vector. You can think of it as G1, G2, G3, and then multiplied by A1, A2, A3, dot, dot, dot. Okay? And this is this piece over here, that is that piece over here. I can think of it as that way, as a compact notation to write this thing down. Okay? So if I have that written compactly, then I can write this vector A in terms of that. So finally, I have this function which is just equal to G transpose dot with A is just G inverse dot with F. Okay, so I have this rather compact way of writing that expression. So I have this vector F, which is the unknown that I've started out with. Okay, that is essentially equal to G transpose stacked into a column vector times the matrix G inverse times another column vector F. Okay. So, but what is my column vector F? My column vector F is given by this notation over here. Okay, this column vector F, the n component of this S of n is essentially equal to this inner product with that. Okay, so I can think of this as being equal to G transpose dot G inverse dot another column vector W with that over there. Okay, with that over there. So you can see that, okay, I forgot this piece over there. So I can think of this as an identity operator, an approximation to an identity operator. Okay, identity operator dot comma with F. Okay, where the identity operator I is G transpose dot G inverse dot W something. So this is the approximation of the identity operator for non-orthogonal bases. For orthogonal bases, it's very simple to define. We just have to define it this way. But if the basis is not orthogonal, you end up with this being your definition of the identity operator, where this is the inverse of the Gram matrix. Okay, this is the inverse of the Gram matrix. Okay, so is this clear to everybody? That this, in fact, is the approximation of the identity operator in the non-orthogonal basis case. And you can use this to derive equations for you to solve if you want to, given any linear equation of this form, say is equal to B, you can insert this in between. Okay, you can insert this in between, and then insert an identity operator in here, and then you will have L G transpose dot G inverse dot W F is equal to B, and then you can multiply this equation by W transpose W, okay, multiplied by a column vector consisting of W, and then the equation you get would be W L G transpose, and then you can call this the entire thing you have over here, okay, your AN, your A if you want to, because this is just a column vector, is equal to B. Okay, if you multiply this equation by that, you can call this entire thing A, and this is essentially a matrix equation because this is a vector W times another column vector transpose. So this actually forms a matrix system. So this is actually something like A equals B. And after you have summed A, you can always go and find your unknown F. You have this operation over here, or you can substitute this indirectly because this is just A. Okay, you can think of this as your A, and then you get your F back very easily. Okay, using this kind of idea. This kind of idea embraces both the idea of finite element method for differential equation as well as method of moments as commonly used for integral equations. Okay, all of them fall under this subspace projection method. Okay, are there any questions? If not, then let's just move on and see what we have. Okay. This we have been talking about linear operator equation of such a kind. Okay, sometimes it can be written as LF equal to G, but you can also have eigenvalue problems. For instance, you can have eigenvalue problem of such a kind. Where lambda I is the eigenvalue, and f sub I is the eigenvector. Okay, that is eigenvalue and that's eigenvector. And then you can prove orthogonality quite simply. That if you have a different eigenvector and different eigenvalue, you can actually prove orthogonality by multiplying this equation by f sub I. You get a new equation, and then the other equation you multiply by f sub j, g f sub I. Okay, is equal to lambda I f sub j comma f sub I. Okay? And then if you assume that G is symmetric, if G is symmetric, then this piece here is actually equal to that piece over there. Then Fi G Fj would be equal to Fj comma G Fi. If G is symmetric, this is true. That is the definition of a symmetric operator. So if you don't recall what it is, go back to your basic matrix algebra. Is equal to B transpose A transpose dot A. This has to be true. Okay, you take the transpose of a matrix system, you get this. And if A is symmetric, then this A transpose becomes itself. So we're just doing things like that over here. Okay. So then if you subtract the two equations, you get 0 on the left-hand side minus lambda J Fi comma Fj. Which means that if lambda I is not equal to lambda J, it must imply that Fi comma Fj must be equal to 0. So it proves orthogonality. Okay. You can go through the same proof, very similar to this, if G is Hermitian or self-adjoint. In that case, you can even prove that all the eigenvalues have to be real. Okay, and this works for eigenvectors and eigenvalues in the infinite dimensional Hilbert space as well. Okay.
Excuse me.
Yes.
I think that should be like a not A transpose. Like it should be A on the right side.
Here. A.
I mean in the operator.
A transpose, right?
I think it should be A, right?
No. For general matrix system where A is an arbitrary matrix,
Yes, like a
if you take the transpose of this, it becomes itself.
I know, like, but A is symmetric here, right?
No, A is not symmetric. I'm saying that
Okay.
for general matrix system, this is true. This is true even for when A is not symmetric.
That's how you define.
So you use this to define the symmetric A. If this is self, then A must be symmetric. And we use this to define G to be symmetric. Okay? In the infinite dimensional Hilbert space, we define G to be symmetric in this manner. Okay? Are there any questions so far? So this is like linear algebra, but done in the infinite dimensional Hilbert space. But then we have to always project this Hilbert space into a finite dimensional space in order to do calculations. So let me talk about variational expressions. So let's do a simple case where LF equal to G. And let's assume that L is self-adjoint. Self-adjoint is just a mathematician's name for Hermitian. Okay? But some mathematicians don't distinguish that. To me, I think it's equivalent to Hermitian for linear algebra. Okay? But it can show that an expression such as this one, self-adjoint, or you can also define it for symmetric system too, or symmetric. Okay, if L is symmetric, then we can show that this is a variational expression for symmetric system. If L is symmetric. And then for L that is self-adjoint, we actually have to define an adjoint part of the solution. Okay, LF minus F adjoint G minus G adjoint F. And we can show that this is the case for self-adjoint problem. Okay, sorry, this should be complex complicated. For self-adjoint problem, And that we can show that this is actually using energy in the product. This is actually using what we call reaction in the product. Okay, both of them are variational, and electromagnetics, we have two kinds of inner product. We can choose inner product to be of this form, then it usually has a physical meaning of energy or power. Whereas if you choose an inner product of this form without a complex conjugation, we call that the reaction between two quantities. So I will call it the reaction inner product. And I can prove that the solution to a linear operator equation is a minimum of those reactions. And those reactions can be thought of as a functional.
How do you show that those two expressions are variational?
I'm going to show it next, okay? So I is a functional of f. Functional means functional of function. So I is a functional of f. I can show that it's very easily. Let me just show the symmetric case. And then you can derive the solution for the second case. Let's assume that LF exact is equal to G. Okay, LF exact is equal to G. And we have found the exact solution to this linear operator equation. We let F be F exact plus delta F. The small departure from the exact solution. Then if you substitute into this equation, you will get 4 terms. Okay, you get 4 terms. And if you don't like to do the substitution, you can take the direct first variation. The direct first variation of this function now with respect to a change in f using variational calculus is just equal to delta f L f exact plus f exact L delta f minus 2 delta f g. Okay, if you take the first variation of this equation, you get that equation. You can also do direct substitution and collect all the leading order term and then cancel out the leading order term and get this. But I just take the first variation and get that. Okay. If this is a variational expression, what it means is that if I plot this functional I as a function of f, this is a cartoon picture, because f is a vector, I cannot actually draw it. But what it means is that there is an f exact value that will make this I minimum or stationary about that point, and that if I have any first variation, delta f, if I try to vary about the stationary point by adding a delta f to this, the first variation in delta I is equal to 0. Okay, because this is a stationary point. About this point, delta I is equal to 0. Okay, if I do a linear change in delta f, there's no linear change in delta I. Okay, so if this is really true, then the first variation has to be 0, because that point is stationary. And if you look at this equation then, if L is symmetric, then this can also be written as delta f L f e. Okay, so this term can be lumped up with this term together. But delta f is arbitrary. It's an arbitrary vector. Okay, so you have this term plus this term plus this term must be equal to 0. There's a factor of 2 here that cancels a factor of 2 there. And from this you conclude that L exact must be equal to G. Okay. So you easily show that the first variation of this expression about the exact answer has to be 0. Okay, about the exact answer has to be 0. Okay. Aditya, you get it? Okay. So this is the spirit of the variation expression. So instead of solving the linear operator equation, you can think of the linear operator equation as a minimization or the optimization of this variation of function. That is the spirit behind the finite element method and method of moments as well, many integral equation method. And if L is not symmetric but self-adjoint, you will minimize this function L. And you can easily prove that by taking the first variation of this one, the exact solution satisfies the minimum point requirements. Okay. Okay. So there is another interesting thing that is also variational, but not in terms of reaction or energy. But before I move on, let me point out the fact that this expression is quadratic. This expression is quadratic. So this expression is very similar to ax squared plus bx is equal to f of x, not f of x, it's I of x. Okay. So this expression here is very similar. If f is not a function but a variable instead, then it will become an equation something like this. And if you, let me put a 2 here. If you differentiate this, then you get 2ax plus 2b equals to 0. And this equation gives you x is equal to b over a. Okay. So this is for a one-dimensional equation. The variation expression would have looked something like this, and you would have found the minimum very easily by solving this one-dimensional problem. And what we're going through is actually repeating this exercise in infinite dimension or multi-dimension. And this expression is actually quadratic because there's two f's over here. This is linear in f, and when you do the minimization, you end up with this equation over here. So let me talk about Jones quotient next. And this was done by Jones in around 1956. Okay. So usually, sometimes we are not interested in the field itself. We are interested in the measurement. Measurement can be written as a linear function of the solution. So we solve for this solution. And that is what we are interested in. If we are solving this original equation, we might have solved this original equation with the method of moments, finite element method, and so on. But we are interested in this measured quantity. Okay, we are interested in that measured quantity. So we actually want this to have the least error. This is something of interest. It could be the input impedance, it could be the radiation pattern, it could be the radar cross-section of some sort. Okay? And it's usually related to some measurable parameter. And since these functions are usually a linear functional of the solution, you can write the measurement as something like that. Okay, once you have the solution, you can find the quantity in this method. Can we write a variation expression for u instead? It turns out that Jones came up with such a variation expression. So if you can write this as the linear functional, this is called linear functional. So it's a linear functional of f. You have to define an auxiliary problem. L of f is equal to h. Okay, this I would call the auxiliary problem. Maybe 2L, auxiliary problem. Okay. And then I can define a Jones quotient that looks something like this. F A G H star F over auxiliary solution times LF. And this is for L is self-adjoint. Okay, L is self-adjoint. But if L is not self-adjoint, you can also define a Jones quotient in this manner without the complex conjugation. And in this case, U would have been H comma F without the complex conjugation. Okay, and this is for symmetrical. If L is symmetric but not self-adjoint. So you have two kinds of Jones quotient to use. And this is very good for people who want to do certain calculations for certain measurements. And how can I prove that U is variational? That if you make a first order error in your solution, you have a second order error in U. Okay, which means that if you have delta FA, it means that delta U is equal to 0. The first order error is 0 if you make a first order error in your solution. So let me prove that. Let me prove the case for the symmetric case. You can go to the self-adjoint case very easily. To prove that, I will have to do a cross multiply. H comma F.